and we'll get straight into the program. Our next speaker is Peter Lundqvist, systems engineer at Arista Networks, where he works with design and building large-scale data centers. Before joining Arista, Peter worked at Juniper Networks and Cisco Systems, and he focused on routing and QoS. So please do join me in welcoming Peter to the stage.
Not the best start when they're naming my competition, really. First, I'm going to take a picture of some shitty questions to remember who you are, so I can hate you for your life. All right. Okay. AI feels a little bit odd, me as a person here talk about AI. Obviously, there should be some AI simulation on me to do with it. So let's see here the expertise level. How many here have worked in depth in any AI platform? Please raise a hand. Oh, shit. All right. How many here thinks this is interesting? Raise a hand. How many here had drank coffee in the last 50 minutes? Please raise a hand. All right, no, you're alive. Good. These are the topics. I not in any way claim that I am an AI guru. I work for a company that build a shitload of AI complex, so that's sort of my expertise, right? But we need to start somewhere, so that's why I'm going into the background in regards to the AI concept, and then I go into what's the sort of expertise piece that where I come from, which essentially supporting the network that are AI platforms. So any objections to that? Well, I don't give a shit really, because this is what I'm going to talk about. Right, so definition of AI. I also have wear a t-shirt in my previous slides, AI, that is 10,000 if then else statement. No, it's not. No, it's not. That's machine learning. So there's a big difference here between machine learning. Many of you have done machine learning without even knowing it. The definition of machine learning is still in the AI competence because you can have a platform that helps you out. But most of the cases actually stake in learning, and that's the definition of machine learning. So in many ways, people talk about complex AI and they talk about weak AI. And these are not words that I come up with. These are actually words that be named in the industry. Weak AI is machine learning. There's a clear definition of something that you want to achieve, and there's a clear definition about what the content is going to be when you sort of deliver it. AI is all about artificial and mostly neural networking, which means that you sort of let something else create something, and hopefully one of the spin effects actually going to achieve what you want and desire. So that's a big difference between ML and AI. I've been 9 years in Arista. I'm not going to go into what I did in Juniper and Cisco. Hopefully that was good stuff. I don't know. I think there's some competition here that can say if I were good or bad. I couldn't care less. But in my 9 years in Arista, I mean, I've been shitload of machine learning. The AI topics now is recently just 1 or 2 years old. However, everything of this is mathematics. Mathematics is one of the oldest written language in the whole world. You have English, France, whatever, total different grammar and all that, but mathematics is the same all over the world, and AI is all about mathematics. So there's no hocus pocus, just a little bit of hardware and some people with bird and roller skates that have been able to utilize it. That's the AI concept. So if we look at the classical way of machine learning is that you put up a camera somewhere like Sveavägen, and you put it up there and have your input. The input there is well defined. You know there's a road, there's black and red and white cars, and maybe you care about the brand and stuff like that. And the outcome, what will be the weight, is that you're going to calculate how many red cars, how many blue cars, how many are speeding, and so forth. So it's a well-defined input and output. That's machine learning. Machine learning helps you with total amounts of data. So that's really the only thing that machine learning has in common with AI. There's a tremendous volume of data. Deep learning is a totally different beast. That is that you still have the same freaking camera and sensors. You take in massive amount of data, And that data then can spin with side effects that you don't know. So that means that, for instance, the camera indicates that, okay, there is an Italian license plate, there is a Finnish license plate. Maybe I should learn to speak French, or at least understand French. That is what AI is doing. So AI by itself, because it had so much of data, can spin out the effects that sometimes are desired and sometimes not desired. And that is what it needs, this tremendous amount of computing power. Deep learning. Deep learning is neural networking. I quit my studies '94, and I think I at least had 10 points of neural networking already then. How many here is old like me, 50 plus, and are aware of neural networking? Please raise a hand. These are the old guys close to retirement, so now you know that. So again, many of these words are just buzzwords. Now we're talking about deep learning, but deep learning is actually neural networking. So if you take up an old book, and actually did this 1 year ago when the company told me, Peter, we need to go out and preach a little bit of building AI networks. I took my old book, and I mean, it's neural networking. It's using words like gradient descent. It's using words like weight. So all of that is actually not really news, right? This has been around for some time. It's just that now it's hot and heavy. By the way, how many people think this is hot? Please raise your hand. So why are you listening to me if you don't think it's hot? All right, so a complex model of this, of course, if you're going to go into the data part of it. The whole point with an AI pipeline is to calculate to the minimum loss. The minimum loss that you think now we have achieved sort of the goal. That means that in theory, you drive a car over and over and over again on Highway 101, and when it sort of, manage to do that without a car crash or anything like that, then you think this is an acceptable loss, and Elon Musk gets richer. That is sort of high-level definition when you think that acceptable loss is acceptable. The calculation of f and x here is sort of a closed loop, and this goes on and on and on. The complex piece here is when you add parallelism, and that is what I'm going to talk about in a few seconds. I have made this slide purposely boring, because I don't know anyone that really thought that derivative of a function was funny. Right? How many have worked with derivatives? I see a few people don't raise their hand. Are you saying that you've never done a math lesson? Derivative is that boring thing where you calculate a curve, and the curve endlessly had a loop, and then sometimes around something, then if it goes close to zero, then it's all done. This is what AI pipeline is in brief. It uses the derivative of a function, and in order to have the algorithm, it creates something called descent, gradient descent. Gradient descent is a little bit fluffy word, because gradient descent means that actually it's probably the only thing in the humans add to this process, because that's essentially what you say, enough is enough. I think you have now done enough, Mr. AI, and the code has delivered properly what you want to do. It seems to be by the projects that we have run that AI by itself, because everything is on the internet, right? It can pull in immense amount of data. So you come very fast to something called local minimum. Local minimum, where sort of you can stop and start by a red light, and you know all that stuff. But if you, obviously they want to make it more adaptable. If it rains, if it's foggy, if it's snowing and stuff like that, that is the next piece to come into the global minimum, which is the sort of the ultimate goal. And in order to come to the global minimum, that is where you allow the AI to really go funky, right? Go high wire, because it needs to take input. And that's where surprisingly things can happen, right? They can, AI suddenly decides to take a law exam and stuff like that, because you don't add any delimiters to what the code's gonna do. Previous curve was a one-dimensional, right? When you apply this mathematics, it's actually a three-dimensional model. So the gradient descent is on millions of input nodes. So it's very easy to show this stuff, right? But in reality, the three-dimensional core, or four-dimensional, or fifth-dimensional, depending on how much of ArcGIS you have watched in your life, that is sort of how this looks in reality. I have most experience from the ChatGPT. I think ChatGPT 4 has, I think these are put in trillions, but imagine it's just immense amount of computing nodes that you add to this code base. So let's look at the ChatGPT. This is an example I have. I had done BGP for most of my life. One of those questions that when I interview people is always around the marker field. Because if people knows the marker field, then they had done in-depth BGP. And this was actually a big surprise for me because I've interviewed people for 30 years. I have coded very hard, at least for 15. And this is probably the best answer I ever have seen. It is just astonished really how it is on the money here, because what the market field is. And this is all about the AI's training model. It has so trained and trained and trained and trained and trained, so it ultimately gets better and better and better. And that is sort of a little bit scary part for us humans, right? Because machines, they don't stop, right? They will continue to try to adapt. I don't say that it will always be better, because that's something for politicians and whatever to decide, but just inbuilt model of AI is that this is a repeatable loop to always try to exceed. We humans are lazy, right? You manage your exam and then, shit, I don't want to have a single derivate, whatever, question all my life, right? Machines doesn't think like that. And that is sort of the things that AI comes to show. Then also, it just gets better the more questions you add to it. The more questions you add. I can agree you don't need to be an AI to understand that Hammer will beat the shit out of you Gordon in the next derby, because everyone knows it. But the more thing you work on it, the more thing that AI will adapt. And that's the interesting piece here. The more data you add to it, actually the better it gets. Is there any you Gordon in this room? Please raise your hand. I don't ever want to speak to you in my life again, Uwe. All right. Now we come to the points that actually affects you if you are a networking guy. And that is how these nodes interpret with each other. And essentially, there's a whole bunch of models from broadcasting to whatever. But the two most common ones are all reduce. All reduce means that you do mostly all your calculation to receive your gradients ends on a small amount of data locally on those GPUs, right? And then that summary, which is the loss acceptable, that's the one you share with all other GPUs in that cluster. So that is sort of a summary. Think of it like a routing network that do summaries between areas, right? Exactly the same thing. The game with this, obviously, is that you achieve faster with the outcome, because you calculate a piece of it. That piece is seen as truth, and that's the stuff that you export to others, and the others one will see that's a input data for them, which is the input ultimate truth, and it starts from there. So this is probably the most common algorithm when you have these AI clusters. The total opposite is all gather. That is when people like me that come from networking field are really getting greedy, because those will create gigantic data centers. There's a massive amount of data where more or less the GPUs compete with each other. And the summaries are really on a more global base. So both of them are very intensive for regards for the networking, but the altogether is you need to have really thick pocket like the big titans to go with that model. The most common one is all reduce. So what does that mean for the hardware? Well, I talked about something called GPU. I'll come to that in a minute or seconds. But what does it mean is that you have one node that calculates something, and then you can share it with other hardware. And there's a mathematical theorem that says that if you have a problem, chop it into small pieces. If you chop it into small pieces, all of them are calculated, the sum of it will be the correct answer. So that is like you're building a car. You don't need to let one guy build everything from stancing the plate to adding code to the steering wheel. Except that you have one is adding the steering wheel, one is painting the car, and so forth. So this is sort of the multi-GPU way of doing it. And obviously, that is the most common piece when these AI clusters grow, because they have a tendency to grow. Difference between CPU and GPU. How many here have had a GPU in your home computer? Everyone, right? It comes from a graphical card. The graphical card is excellent in parallelism. It's not particularly good if you're going to look at something very specific irregularly, then the CPU wins the show all the time. But GPU is the next best thing in sliced bread in parallelism and sharing data. And that is why this has been around. GPU, I think, actually own a little bit that name. It was invented by NVIDIA. But I would say that everyone talks about GPU in the AI business. But essentially what it is that it's just a CPU created for parallelism. So by far different than really a CPU. What you will see in the hardware market is that people will create CPUs and GPUs will fairly be the same. It's just going to be the runtime kernel in them that will differentiate so that one is better in parallelism and one is better on other tasks. Most common thing with this hardware, you can see that there are at least 8 to 10 GPUs per board and 1 or 2 CPUs. So that is the most common if you just do one hardware line card. Now we're going to come to the networking piece. All of you now consider yourself AI experts, so I can pass on. Do I have to take it one more time? I'm not going to take it one more time, but just want to be polite, right? Because they asked me to be polite, Peter, and don't say the nasty things about Juniper and Cisco and so forth. All right, so networking piece. What is it? Is there any expert in here on InfiniBand? Is there anyone that knows about InfiniBand? I easily 15 people here, go to them, because I don't give a shit about InfiniBand. So I'm not going to even talk about it. So find them out and get your lesson in InfiniBand. I'm an Ethernet guy here, so that's it. First of all, it needs a lossless network. And what does it mean with lossless? There's nothing about QoS in here. It's actually, everything is here is to prevent that you actually have a collision. So lossless means that, okay, you're going to take care of burst, you're going to have a graceful handling. The latencies needs to be consistent. It actually doesn't need to be super low, right? But it needs to be consistent, which means that you need to be able to take care of burst. It needs to be without collision. And collision here is not really congestion. That is, these networks usually have a lot of ECMP, so you need to be able to have not all of this traffic end up on the same link. And the last piece here, you need a lot of visibility with telemetry, but I wouldn't say that particularly advanced just for AI. I mean, any data center or core needs to have telemetry dish. I mean, that goes without saying. So what is RDMA? This is really the heart and soul of the GPU. That means that there's a way to bypass the CPU and the Linux kernel totally, and the GPUs can peer with each other directly. Actually, it just bypasses the CPU and the kernel. That means that it reads directly into a memory on another host. That is what RDMA is all about. And this is truly the heart and soul of everything with Haspi GPU, because without this RDMA, you essentially take down 30% of the horsepower, because you add the kernel that the kernel can't really be that fast. You need to have direct memory access. So this RDMA was actually previously designed just for InfiniBand. Ethernet had a good taste to conserve something called RoCE, which essentially is RDMA over Ethernet. These days, no one builds a proper data center on layer 2. So it means that you need to encapsulate this as an IP packet with an UDP header, and that means that you now have RoC version 2. That essentially adds IP to that existing packet. That's it. I know seen presentation when people go endless about this. All it does really is to add an IP header to an existing RoCE header. So this is very common here to be able to have a networking piece so that GPU X and GPU I can communicate with each other without any disturbance. So that's what RDMA is all about. Can you have a network without RDMA? Of course you can have. But that is a little bit like elda för kråkorna in Swedish, because essentially you add in delay. You add in delay because you will need to have a Linux kernel that needs to find it out, okay, maybe that should be in a graphical kernel that needs to process it. Flow collision, that is probably the biggest problem when they're building these large data centers, because everyone talk about, yeah, but 5 tuple should work. Who knows about 5 tuple here? Raise a hand. So 5 tuple means that source, destination, address, source, destination, port, and something. That is what your hardware out there can distinguish a packet and a session from each other, and thereby allow load balancing. The problem with AI loads is that there's not that much of entropy here, right? Everything comes with the same IP address. Everything comes using with the same ports. So it's actually a little bit just in the data that distinguish it from each other. And by the way, most of these flows here are on UDP. So it's not really a TCP sequence number either. So it's not that much of data here for your fancy ASIC here to figure out good load balancing. So that is one of the challenges. The way to battle this is that you have algorithm in ECMP that can reach the bandwidth that continues now going on ECMP. So this is not multi-link PPP where you spray packet. But what it does is that, okay, I think all of this belongs to the same session, but member A of my ECMP is totally saturated. I need to move stuff over to member B and C and D and so forth. And that is what DLB does. There are varied standards for the different way of doing DLB, but most of them, what people do is just monitoring the bandwidth, and then they sort of push over to another link, which is least usage of it. This is one of the absolutely most important thing if you have a leaf spine and you're doing AI. But elsewhere, you will find that you're actually going to have congestion, real congestion, because you can see that because of the low entropy, so much of the traffic here will end up in the same link. Jesus Christ, what time flows by. LBN. This is mostly the most funkiest piece here. How many here has heard about ATM? Please raise a hand. How many here knows about PVC? There's a whole shitload of old people in here. So what this means is that this is going to solve 2 things. First of all is that you're adding a tag on your inbound Ethernet port where the server is, and another tag on the port that goes to the spine. The spine has exactly the same number. That means that you can, with if you're very skilled or you do a script for it, can actually force that every package that comes in from GPU 1 always will end up on GPU 1 on another spine, on another leaf. So that means that you can create group, which is very important, like for the all reduce, right? Because that means that you can group clusters irrespectively of the hashing. But it is a little bit boring, right? Because it looks very much like old PVC networks, and it leads to not. If you don't have any way of proper management of this, you will find that this is just for the titans. Next problem is incast. Whatever you do, you will run into incast. And incast is that whatever you will find out that one GPUs or a whole bunch of GPUs for unsuspicious reason ends up on the same destination GPU. And then it doesn't matter if you don't have any over-provision, because you can't have over-provision in this network. That means that you will have collisions here. So how to handle that? Well, you have the pulse frames. Problem with pulse frames, they are layer 2. So it's not going to be beneficial that much for you, because these are normally most routed networks, right? So this will just be in the first hop, but it will not be, achieve anything for you. Congestion notification means that you're going to sort of simulate the pulse frame by adding certain bits to the distro code header, and I will come to that. And the last thing is deep buffers. I don't care what you guys say. There are many here, you don't need the deep buffers. Well, you sure as hell going to miss buffers if you don't have anything. But if you have buffers, you can call it that you don't use them. That's the big difference. It doesn't matter, right? These are the same rules that apply for if you have storage. So, ECN bits. That means that these last annoying bits, because you have had 8 bits that you earlier, 6 bits for the disco header, the last piece of ECN says, I understand ECN. And the second one is, I have congestion. So it's not that advanced thing to do, right? But this means is that you actually can, if you have a UDP network, you can actually mimic the behavior of TCP windowing and TCP slow start and stuff, because you can actually notify that, hold on, take a minute, I'm oversaturated, you need to do something about it. So that's how it works. That is that each server needs to understand these ECN bits. The networking piece then adapts and adding certain threshold, call it weighted red, whatever. they don't necessarily need to drop the packet, but they need to inform when you're coming up with a certain load on a link, set the ECN bit. That means that the receiver side sees it, and that is what is going to acknowledge back, because anyhow, if you don't have TCP, UDP will have an application acknowledge, and thereby you have sort of a simulation how TCP works. So this is one of the, you can say this is QoS, but there's actually no congestion in the network here, right? Whatever you try to do here is to avoid congestion, because if you have paid billions here for all those expensive GPUs, you can't have reruns if you only have 3 or 4 days, and maybe you're renting an AI cluster to do your simulation. That doesn't fly, right? So this is all about efficiency. Buffering. Who thinks buffering is bad? Raise a hand. Because I'm going to meet the one that says it really here, and I've taken a photo, so I will remember with, but I will do. Buffers is all good. There's nothing wrong with buffers. Architecture for AI networks. 5 minutes to go. Yeah, you can either build single-tiered or you can multi-tiered. Single-tiered is obviously when you start small. Start small. Start small, what does it mean? Well, if start small means 64 or 400 gigs locally, whatever. By the way, please remember here, I don't have my vendor's name on the switches, but you can try others and fail. Mines are better, but I will not, I can give them a break. So this means that essentially is that these are the bigger pipes model. I have really not seen any AI from NVIDIA that doesn't use at least X6 Connect 6, right? Which means that 100 or 200 gig. Or you connect X7, which means that you have 400 gig. So these are fat pipes all the way down to the server. This is good. There are boxes here, Tomahawk and similar, that actually doesn't have that much of buffer. That can work if you are on a leaf side. But the thing here on when you build on this type of network due to the incast, and I have built this data center now for 9 years, is I usually put buffers on the leaf and put a pretty dumb spine. Here is actually opposite, because the spine is the key here, because that is what the parallelism is we're going to see. So there you can run into incast. So actually you need to have more buffers in spine here than leaf. So that is sort of a new thing, at least for me. Most of the time here you end up in chassis. And the chassis needs to be at least a water celification here, because that means that you have a fairness to it. So if you're not going to build a leaf and spine, what essentially you do is that you're taking these devices then and connect the others. Again, there's no such thing here as an over-provision in the AI world. That is the whole rule. Actually, you try to have more bandwidth towards your leaf and spine than actually towards your access side. And that's totally different. Usually data center you build with an over provision of 1 to 3 or 1 to 6 except storage. But that is sort of how you build these type of networks. Right. I think I'm reasonable on time, right?
Perfect. So,
any question?
Any questions for Peter? Anything?
Of course, Abrahamson has a question. I mean, I could bet on that. Yes, they're usually a large packet, because what it does is that it actually works in containers. So actually multiple tasks for that job. So you will see around, if you put 9K as your MTU, it will fill up. And that's actually a good stuff, right? Because then you don't end up in a PPS problem on the switches, right? So the bigger packet, the bigger. The smallest thing I've seen is probably around 600.
Can we have the microphone for the Menti, please?
Feels like a rock star because I can't see a shit in this, but maybe that's good. I don't know. But all of you look amazingly good.
Can we have one of the radio mics switched on?
There we go.
Shoot.
Someone who wants to be anonymous, so they asked it on Menti, want to know why you didn't ask ChatGPT about the results of Hammarby and AIK.
That person, I will buy a beer on my own expense tonight, really. That was the best question ever.
Okay, seems like we should end on a high, so please join me in thanking Peter for a fantastic presentation.
Thank you very much.
Thank you, Peter.